Hello everyone and welcome to this webinar. So this is our webinar series called Runtime Insights, where we try to present a new topic quite frequently, and so far we have done this every month. And today I'm going to talk about our extended support for where we've added Azure RTOS ThreadX streaming trace in our Tracealyzer. So first, a little bit about myself. So my name is Kristoffer Martinsson, and I work as field application engineer at Percepio. I have been working for more than 15 years with the development tools for embedded system, and I have been focusing on debug and trace tools. Just a very quick agenda for today. So I will give a presentation, and where the most of the part will actually be a demo, and will be roughly 25 to 30 minutes, and then there is time for Q&A. And if you have any questions, please use the chat to type your question, and you can send in your question anytime during the presentation, but I will try to answer them at the end. And the question does not have to be specific about the topic here today. It could be more general about RTOS and RTOS tracing and so on. So first of all, I want to mention what we have support for related to ThreadX up until today. So we have been supporting ThreadX for quite some time, and we have been supporting the built-in trace hooks that are available in ThreadX, and they are called Tracealyzer, and we have been supporting this for snapshot tracing. So with this snapshot tracing, the trace events are stored in a ring buffer in RAM, and the size of this is typically measured in kilobytes for a Cortex-M device. And since the limitation of the size of the ring buffer will also set a limitation on the length of the trace. So typically you can have a trace in maybe 100 millisecond or 200, or if you have a large ring buffer, then you can record for a trace for 1 second. So with this setup, you can more or less, we can support ThreadX tracing with any debugger, since the debugger just needs to be able to save the content of the ring buffer and save it to a file that can be opened in Tracealyzer. So this is what the support that we have for ThreadX up until today, but we have seen many requests on ThreadX where they would like to do streaming trace. So we are now adding support for that. So to be able to do that, we had to create our own recorder library. And with this, we can add streaming support, but there are also some more benefits. For example, we have added more detailed tracing. For example, we can see in the trace if you have a call to a semaphore get, for example, if it fails because of some wrong parameters and so on. We are adding some trace events that are not available in ThreadX by default. And we're also adding more flexible user events. So you can create what we call user event channel for grouping your different user event. And you can also send out formatted strings that are not possible with the ThreadX user event. And some more features that we're adding is like stack monitoring. And we actually also add a more memory efficient snapshot tracing. Okay, a little bit more about streaming trace. So streaming trace, we have had this functionality for other RTOSs like FreeRTOS for quite some time, but now we are adding it with version 4.6 in Tracealyzer. We are adding also this for ThreadX. So we support many different streaming interfaces. We call these stream ports, and some of the more popular one are, if you have a J-Link, you can use RTT. If you have a Cortex-M device with some other debugger, you might be able to use ITM. but we might have other streaming interfaces that's possible, for example, serial or TCP/IP and so on. The main benefit with streaming trace is that unlimited tracing is possible. So you can record for minutes or even hours if needed. But I will come into some of the possibilities you have with streaming trace. I will come into that with in my demo. So, but we also support something we call live visualization. That means that some of the views in Tracealyzer are updated during recording, which means that you can, for example, plot the variable or something like that in a view, and you can monitor the CPU load and so on while you are actually recording your trace. So that was the last of my slides here today. So I'm going to switch to my demo. And actually, my plan here today was actually I'm going to start and show you a little bit how to set up streaming trace. So I have here, I'm using STM Cube because I have an STM device, and I've created a project here with ThreadX that includes a demo application which actually simulates a machine, you can call it. So there is a motor task, there is a HMI task and a control task and so on. So actually, first of all, I just would like to make sure that this application is working. So I'm just going to start a debug session here. And it takes a little bit of a while to start the debug session, but I can start the application. Actually, we can see here in the console that it's actually outputting something here from my application, and I can halt the application, and we can see that in the ThreadX list down here, we can see that we have some threads. So as you can see, we have a motor task, HMI task, control task, etc. So we have a working ThreadX application in this case. So now I just want to show you what you need to be able to add tracing support on this application. Okay, the first thing needed is that we need to add the source code for our trace recorder library to the application. So actually, I'm going to create in my project here, create a new folder that I'm going to call Tracealyzer, like that. And I'm actually going to create a few subfolders here, one for the source, one for the includes, and one for the configuration files. And then I'm going to copy the recorder library code to my project. And the code for the trace recorder library will be available in release when you install Tracealyzer, but it's also available on our GitHub page. So I have the code here on my local drive here. So I'm just going to first just copy the source code, and I'm going to add it here to the source folder. And then I'm going to do the same thing for the include files. And the same thing for the configuration files. So the configuration files are just templates with some default configuration. We will need to do some changes to that later on. So now we have copied the code and header files to my project. And the next thing, so this was just a basic trace recorder library. We need also to decide which stream port that we would like to use. So what streaming interface do we would like to use for streaming the trace data? And as you can see here, I have a folder called stream ports, and here are the different stream ports that we have built-in support for. And today I'm going to use the J-Link, so I will use RTT here. So I will also add this code to my project, and also include and the configuration. Like that. And the next thing, of course, is that we need to make sure that the compiler finds our header file. So I need to add the include and the configuration files to the include path. So I will do this like that. And there are a few more things that is needed. for getting tracing working. And the first thing, or the next thing I'm going to do, is that we need to enable the default trace macros inside of ThreadX. And that is normally done in a file called txuser.h, which is the standard file in ThreadX that you have a lot of different configuration options for your ThreadX. And there is one called enable event trace, and we need that. So I will make sure that this one is defined. And then there's actually one more thing here, because we would like to have stack monitoring enabled, and then we also need to enable this one. Enable stack check, like that. Okay, that's the TX user. And another thing that is needed is that we need to add, include our trace recorder header files in all the ThreadX files. And a suitable place to do that is actually inside of another standard ThreadX file called txapi.h. I'm going to open it, and I will add this at the end here. I will include PRC recorder. All of these steps that I'm doing right now will be described in the user manual at the release of 4.6. So now we've included that, the tracerecorder.h, and there are a few more things. As I mentioned in my slides, we are actually adding some more detailed trace. So the standard trace hooks for ThreadX is not enough to get all the details. So we are using some compile time instrumentation to do this. And to enable this, there are two things needed for my project. First of all, I need to make sure that one file is included in all code or source file in the project, and it's called trccti.h. So I will add that to the include files. And I also need to add a preprocessor macro so that we can determine in what file we are in. And I'm going to do that right here, like that. So this will create a macro where it will be inside and then a file name here. So we can just see in this when we're building the application in what file we are in, like that. And I will close this one. And now we are, I will not rebuild right now because we are not really there. There are two more things that is needed to enable streaming trace here on the ThreadX application. And the first thing is that we need in the code have a call to a certain function to enable or initialize the trace recorder. And it's very, very important that this is done before any calls or the creation of any kernel objects. And the creation of kernel objects in ThreadX is always, or you can say it's always done here in a function called tx application define. So this is automatically called by when you're starting the kernel. So at the entry point of this one is a very suitable place to add our call. So I will do that xtrace enable. I will call here, and I will have a start option called start from host. There are a few different start options that you can use, but this one will make sure that you initialize the trace recorder library, but the tracing is not started until I from the host, so from Tracealyzer, actually start the trace recording. But it should be a small n here, like that. Okay, let's save that file. And then we also need to do some configuration of the trace recorder. And those files are available here in the CFG file here, or a CFG folder. And there are a few things that is needed here. We need to include the header file for the MCU that you're using. In this case, it's an STM32L4. Move that one. And then I need to tell, okay, a hardware port we need to define. So this is Cortex-M device. So I'm using that. And then it is streaming trace. We would like to do like that. There are more configuration options here, but the default one is fine for me. And then there is one kernel specifics here. We need to define the CPU frequency or the MCU frequency to be able to get accurate timestamping. And my MCU is running in 120 megahertz, so I specify it here. There are more configurations that's possible here, but most of the time the default options is possible to use. So I'm going to rebuild my application, and while we're waiting for it to build, because it takes roughly 20 or 30 seconds, I would like to show you what you need to do in Tracealyzer to do to stream the trace data to Tracealyzer. Yeah, I'm going to go into the trace view and open live stream tool. And here we have a settings tab. And you need to select the streaming or the target connection here. Now it's selected Azure RTOS. That's what I'm going to use. But as you can see, there are other options here. But I'm going to use Azure RTOS, so that's fine. And then there might be some other options here that is needed. But in my case, the way I've set up the project, these are just fine. There are more information about this in the manual for Tracealyzer. And it's also very important that if you're using RTT with a J-Link, that you get the correct J-Link settings here. So you always need to select the correct target device so that we can connect to the device. And you also need to specify the debugger interface and the speed of the debugger interface. And here I can mention that I'm using 4 megahertz here, which is actually quite low. But that is because I'm using as an onboard J-Link, it doesn't support higher speeds. But if you have a standalone, you should have this to a high value as possible. So a normal J-Link base supports, I think, up to 15 megahertz, and then you should try to use that to get as much bandwidth as possible. So this is all you need to configure tracing here in Tracealyzer. I'm going to switch back to STM-Cube, and as you can see, my application has built, so I'm just going to flash the application right now. So I will start the debug session and it will flash. And hopefully I've done everything correct, and I will just start the application and I will switch to Tracealyzer. So now we can connect to the J-Link and the target, but you don't need to have a debug session running at the same time, but it's possible. But I will start it. And as you can see now, we are the tracing starts. And we see here in this live stream view, here we can see a graph of the CPU load, and you can also see the amounts of trace data. So the amount of trace data varies over time. It depends on what is going on in the application. Sometimes we're only at 10 kilobytes per second, but sometimes almost 150. So we can see here the number of trace events that we have recorded and so on. And I just want to mention one thing. If you are using this tool and you down here see something called missed events, then you should really follow our troubleshooting guide to make sure that you don't have any missed trace events, because that's bad. And then you cannot really trust what you see in the trace. As you can see here, the views are, or some of the views are actually updated during runtime. So you can see, for example, the CPU load here over time and so on. And there might be some other views here that you can have to be updated during the recording. We call it live visualization. So now I've recorded for a little bit more than 1 minute. So now I'm happy with that, and I will just stop my trace recording, and we can see the trace. So I'm going to close this window. And now, more or less, if you have been using Tracealyzer before, you can do all the normal things that you normally do in Tracealyzer. But I'm going to talk a little bit about what actually are the benefits of streaming trace. What can you do with streaming trace that might not be possible with snapshot trace? And one thing is, of course, if you would like to profile your application and for a long period of time, of course, that's not really possible with snapshot trace, since it's limited to a few hundred milliseconds maybe of trace. So that's possible. So for example, you can check the CPU load graph and see how the CPU load varies over time here in the application. So, and if I click somewhere here, we can see up to the right on the selection details, we can see some more details. So this was the control task, and it takes 18% of the CPU load in this interval here, and so on. And it's also possible to do a report of the CPU load, more or less on the average. There's some statistics over it, and you can do that in the views menu and actor statistics report, and it will pop open on my other screen, but here it is. So here you can get on the total trace, you can see some of the the CPU load here over time. And other things that might not be really possible to do is with a snapshot trace. If you would like to verify the timing of something, that doesn't happen that very often, or it takes quite a long time. For example, we can see here that if we just take a look at the HMI task here, it's running roughly here in a period of 100 millisecond. And so if you would like to analyze something of the runtime of the HMI task, it might not be possible with snapshot trace, because it's very difficult to capture more than one execution of it in a snapshot trace buffer. But with Tracealyzer here and streaming trace, we can record for minutes, so it's not really a problem. So for example, you can take a look at the if you're interested in the HMI task, you can, for example, take a look at the startup time for it. How long does it take until it gets ready to execute, until it's, I'm going to do it, and I'm going to select just the HMI task here. So if you're interested to verify the startup time, each F dot here in this graph represents one execution instance of the HMI task, and you can see that the startup time varies between almost 0 and almost a little bit above 500 microseconds and so on. So as you can see, we have many dots here, but even if it's not executed more than once per 100 milliseconds and so on. So if you have events or things that are happening with a rather low frequency, it's much easier to verify the timing of that using streaming trace. And if you, for example, are interested in one of these and want to look further, you can just double click on it, and in the trace view here, you can actually, it's shown here, this specific events, and you can zoom in here and see what is going on. So the startup time, if you're interested, is represented by this time here before it gets a solid blue line, a blue bar here. So it's the time from it the task gets ready until it actually starts to execute. Okay, and there are for sure other things that similar things that you can analyze with streaming trace that makes more sense. For example, if you would like to analyze how long does something need to wait for a certain kernel object, like a queue or a mutex or a semaphore or something like that, then you can use a similar view called service blocking, like this one, and just select some kernel object, for example, the HMI queue, like this one. And as you can see here, we only need to see the receive. It's only the relevant one. As you can see here, the wait time or the blocking time for the HMI queue, when someone is waiting for something on this queue, varies from more or less 0 and up to 100 milliseconds. And for sure, this will be hard to capture with a snapshot trace, since since maybe with snapshot trace cannot even record 100 milliseconds. So that's one of the things with or the benefits with streaming trace, is that it's a lot easier to verify the timing, especially on events that doesn't happen that very frequently. But there are for sure more things that you can do, and I mentioned in my slides that we also support more flexible user events. And I just want to show you a little bit about that as well. So if we take a look in the event log, here are all the user events. And for example, we can see here that motor, PWM, POS, LP, and so on with some value. So with our trace recorder library, we support something called user event channels. So POS, LP, that's one user event channel. Motor, PWM is another one. So we can send the user event data to different channels. So it's much easier to separate the things and do some visualization and so on inside of Tracealyzer. And one thing you can do is if you're just outputting some data like this one, you can actually plot this in a graph. And I'm just going to show you this one. And it looks like this. I can make it a little bit bigger. And here let's say I'm only interested in those two, for example. So now I'm just plotting two different user event channels here. And as you can see, I can zoom out to see the entire trace here. We can see how the data, how it varies over time. And if you're interested, actually, you can double click somewhere here and that event is actually highlighted here in the trace view to the left. And we can see it was done in the control task. We can see it here. We got this message POS LP 353. So, and by the way, this user event signal plot, this is one of the views that are updated using live visualizations. You can see this during the recording of the trace. Another thing you can do with user events or with our user event is that you can easily create a state machine if you have something like that in your code. I'm going to do a little bit of filtering here. As you can see here, there are one user event channel called system state, and just outputting the state of this machine here. As you can see here, starting, moving, stopping, stopped, etc. And you see the timing here, but here you can easily create a state machine and represent this in the trace view. All you need to do is tell Tracealyzer that this is a state machine. And this can be done here in intervals and state machine. I'm going to add a custom state machine and a simple one and just select system state. So these are the user event channels that are available in my application, like that. And actually now I have two. I had one since before. And here you can see now in the trace view, actually you see the state here. I just need to zoom out here. So here you can see when you are in different states in your application, and you can easily see how long did you spend in this state stopping here. Oh, it was 3.5 seconds. And for sure with snapshot trace, this would not be possible since 3.5 seconds is normally not possible to do with snapshot tracing. So that was some of the advantages with using streaming trace. So if you have been using Tracealyzer with FreeRTOS or any other views, then it will be similar here for ThreadX. So everything you are used to, you can do with ThreadX that we've been used to with FreeRTOS or some other tool, RTOS. So that was actually all I wanted to present here today. So now it's time for Q&A. So if you have any questions, please type them in the chat. So the question could be anything related to tracing and Tracealyzer in general and so on. Okay, I get a question here from Muhammad. When will this be released? Yeah, the plan is in the coming week, I would say. That's the plan. We are in the final testing phase of our release of version 4.6 of Tracealyzer. Okay, are there any other questions? Okay, another question from Muhammad was that can I use Tracealyzer with ESP32 Extensa, which is not an ARM-based platform? Yes, you can. we support ESP32 in Extensa, so that is for sure possible. And there's also another question here, how does Tracealyzer compare to TraceX? Yeah, you can see it in different ways. First of all, in Tracealyzer, you have many more views than you have in TraceX, so you can do a lot more detail and more visualization on things. But the major difference now is that we support streaming trace, which means that we can record for minutes, an hour, and that's not possible with TraceX. There is only snapshot tracing possible, and that's the major things. And then one other thing is, if you would like to still use snapshot tracing, you can use our recorded library. It's actually a little bit more memory efficient compared to TraceX. So storing a trace event in RAM takes a little bit some less bytes than with the TraceX snapshot. Okay, I got another question here. With ESP32, there is no SVD, so does it work with JTAG? Yes, it's work with JTAG. And actually with ESP32 and their development environment, we have a streaming interface called Tracks, which is very specific for ESP32. But that is something similar to Azure RTOS, but it's for ESP32 and their environment. But it's called Tracks that can be used for streaming the trace data to the host. Okay, another question here. With STM32, can I run it bare metal, or having an RTOS is a must? You can run our recorder bare metal for sure. It's possible. But then you are like, it will be user events. That's the thing. You will not get all the benefits of everything that's all the kernel events for sure if you don't have an RTOS, but it is possible. And here and a follow-up question on that regarding bare metal is, then will I still get the interrupt service routines, etc.? Yes, you can. Interrupt service routines, they are you need to instrument the ISR to get information about the execution of the ISR. So for sure it can be done also if you don't have an RTOS. Because if you have an RTOS, you don't get the ISR tracing automatically. You need to add instrumentation at the entry and the exit of the ISR. Another question here, where can I find a tutorial for bare metal? Actually, I don't think that we have one. But I suggest that you contact our support and we will try to see if there is some material or we will help you get it running. But I'm not sure if there is a good tutorial for bare metal. Okay. If there are any more questions, please type them in the chat. I will give you like 30 more seconds or so. Okay, but if there are no more questions, we will end this webinar. So thank you all for joining, and maybe I see you next time. So have a nice day, everyone. Bye.